Am I audible to you all? Let me know, please. Am I audible to you all? I'm sure.
Yes, sir, you're audible, sir.
Right. Ask the student randomly to start video also, right?
Yes, sir.
Okay. See, unfortunately, nobody is responding. Whether the students are only joining and say passively be there, or from student side, let me know. Am I audible to you all?
Yes, sir.
Then why
Yes,
there is
sir.
no response? When I'm asking, there is no response. If you could have given response immediately, you could have gone further. Not getting. Okay, now it's 11:05. We'll start for the discussion on the topic. Right. So in the last lecture, what we have seen the different static characteristics, and now we are about to say quantify those. So in this regard, we have seen that the quantities can be so there are three different approaches. One is the approach one, approach two. We said in the approach one that there is standard input known. Approach two, we are carrying out the experimentation where this true value is not known. And then there are three different methods. Say we have said that method A, B, C. In the method A, we are having the single input where n number of readings are taken, or n number of times the experimentation is done for the same input value. In the say approach B, the type the experimentation method B, in which we have got the variation in the input, and then we have taken number of readings. Say for example 10 each for the input 1, input 2, input 3, and so on. Say the graphs are very briefly shown here, right? And in the approach C, we are having the repeated say experimentation for increasing input and also the decreasing input, that is the ascending order of the input and the descending order input, or say upscaling and downscaling kind of thing, right? So based on these three, how we are going to find the properties that were discussed. So the discussion on the type A experimentation has been done by using these statistical properties. We can take n number of readings and then we find the average, where average is going to speak about the best estimation possible for the given measurement, and which is giving more or less the value inclusive of the true value plus the bias or the systematic error that can occur into the measurement, whereas the deviation of individual error above and below the mean line is going to give the randomness that is present into the experimentation, right? So by means of proper calibration, or by knowing properly the true input value as well as the spread, the precision, we can find out the most desired accuracy. So there is a better control that we can obtain over the precision, whereas the random error can only be found out without having any kind of remedy on that. I think this was the discussion that we made, right? So based on the type A of the measurement, we have seen different properties like the full scale percentage accuracy or full scale, percentage accuracy over the true scale, then precision, bias, and also the tolerance band. I think that we have seen what is the tolerance band for the error, or the tolerance band or the error span and the range that we have found out. So these are the properties that easily can be known with type A. Now this was regarding the actual experimentation, but when the true value is known, we can also find out the bias or the precision, because the difference between the true value and the average, the mean, will be giving the precision that can be obtained, the error that is going to remain constant forever for a given number of readings, right? So we have analyze this type A for both condition 1 and condition 2 with the actual measurement and the standard input. Let me know any difficulty in understanding this one. I have asked you that this question to you in the last lecture also. Right. So if this is say known to you, then we'll go for finding the type B. Now during the discussion on the type A, we have said that we are going to find something called the standard deviation, and with the help of standard deviation we can find out the probability of the error that can be there into the measurement, and then that error based on the probability distribution curve we can find within 1 sigma limit, 2 sigma limit, 3 sigma limit, and so on. Thus we can find out 68.24% and the value of the error that can be there. And I will go to that table itself. Say 68.27, then 0.95, that is 95.45, and say 99.37. So within the sigma plus minus 2 sigma and plus minus 3 sigma limits. So when we consider most of the error that can be accumulated between the 3 sigma limit, we will have the area under the curve is equals to 0.9 or 99.73% of the readings will be encompassed in the area, right? So this is how the probability distribution table is used. So using this, I think we have seen the equations for the analysis. We have found the variance and so on. This was the slide that we discussed in detail in the last lecture. It was some more things on the single slide, but then I have again iterated similar thing on the very first pattern slide itself, that how the experimentation was carried out and how we are going to quantify the different statistical methods or the different static errors for the measurement, right? Then we have gone through the measurement of the linearity. So linearity is nothing but deviation between the actual performance curve and the ideal performance curve that is required from the measurement system. And then we express that in terms of percentage over the full scale, right? Then we also found the hysteresis in the input values, hysteresis in the output values, and the percentage hysteresis present, right? So with this, I think we have seen most of the static properties into the consideration. Coming to the next part, let us see. There are many more examples in the different textbooks. They are very simple. Once you understood the principle, you can also apply the similar things to your experiment that you have conducted into the laboratories. The 4-5 experiments that have been shown to you as a demo, and on which you are going to write the journals. The journals are to be submitted in a group. Say for example, group 1-1. Suppose having 3 number of students, then you have to say submit all the experiments in that group. So that particular roll number 1, 2, and 3. Suppose in group 1-1, they are going to write only single journal, and they will be giving a group viva. So whenever we will have the assessment, the viva will be taken, and then questions will be asked to that particular group like this. So group 1-1, group 2, and so on in batch 1. Similar thing will be followed for the preceding batch and the next batches. Right. So date of submission for the experimentation is given to you. So experiment 1, 2, and 3 I think are asked to submit on one date, and remaining 2 experiments on the next date. So that after your submission, I will check those, and then I will conduct viva and give the gradings to you. That is the inter-assessment for practical will be done.
Hello, sir.
Yes, please go ahead.
Sir, actually, I want to request you for vivas. In coming weeks, we have mid-semester. So can we have vivas after mid-semester? So we can arrange the slots as per your need. And currently,
right.
we are.
So wait. I think the viva for metrology practicals are over.
No, sir. Sir didn't took any viva yet.
Okay.
And she's also planning after mid-semester.
So then there will be a little, at least on experiment 1 and 2 we can have viva. Otherwise it will become, then it will be tough for you then. You take a call. I don't have any issue.
Sir,
if you are giving me the complete week, say for example 1 or 1.5 hours a day for complete 5 days or 6 slots for 6 batches, then that will be fine for me. Okay.
No, sir. For studying for mid semesters and theory subjects, required a little bit time. So
I agree with you. What I mean to say is for conducting Viva, minimum
yes,
1 hour or say at the max 1.5 hours per batch is required for me. Assuming that
yes, sir.
minimum 10 to 15 minutes I am asking the questions, and there are
Yes,
at max 5 or 6 group in a particular batch. So 6
yes,
group, that means around 60 minutes to say that is say 15 minutes 10 to 15 minutes for each batch, minimum 60 and maximum say 90 minutes will be required for single
sir.
batch. So you give me the
After
slots
semester,
after me, it's
uh,
no issue, but you have to plan that within the
yes, sir. Yes, sir.
framework before 6 o'clock, that is in our normal time, preferably
Okay,
after 2
sir. Sir,
o'clock.
we will do, sir.
Right. So I am giving very clear idea to you, so that it should
Yes.
not happen that you may say that sir batch 1 is going for some other practical that time.
No, sir.
Now,
No, sir.
right,
We
right.
will
That's
ensure
fine.
that on that
Right.
particular slot, those students who are appearing for Viva won't have any another
Right.
scheduled lecture or lab.
That's fine.
Okay, sir. Thank you, sir.
All right. So I think we'll continue discussion. I have to give some announcement for their test number 3 and 4, which is likely to be on the static properties and the say calibration part. Okay. So I think you remind me at the end of the class. So I will reserve 5 minutes for that. Okay. Then coming to the next part of it, there are certain numericals into the textbook. You go through the textbook, especially of Doblin, Nakra Chaudhary, and any other text that you can find. Right. So in this regard, I would like to discuss. So this was the problem. This some sample that I have taken from some textbook, just to show that serial number 1 to 12, that is the experimentation is conducted 12 number of times, and there is some information. So for example, measurement of thickness using some vernier caliper or micrometer screw gauge. Right. So this can be now applied along with our earlier discussion, and then you can be asked to find the different properties like accuracy, precision, full scale accuracy, true scale accuracy, what is a bias, then what is a random error, maximum random error, minimum random error, then what is a variance, that is if 95% of the probability is considered for the errors, or say 1 sigma limit is considered, what can be the error, and so on. That I think you will be able to find out. It's very simple mathematical tool, statistical tool you have to apply and find out the answers for. Right. Then one more numerical I want to discuss further. Say once you have found the discussion, the earlier discussion on the slides, you may again recall the way we have devised this particular say configuration. Say input is given on the x-axis. Say this is the earlier pattern. This is the output, that is the measured value or the entity after measuring on the display panel of your measurement device or measurement system, and here it is the input. So into this, let us understand that this dot indicate the actual reading that suppose we got. Say for example 20.1 is the first measurement, the second one is 19.9, the next one, and so on. So this is the spread, actual spread. If I'm going to join this with the number of dots, this is how the measurement is obtained in actual practice. Okay. Then again, to sum up, the mean value will give the better prediction. Say for example, the one shown with the dotted line here, that is the mean or say approximate estimation of the given entity or the given measurement of the block thickness. Let us assume you can take anything, the pressure measurement or temperature measurement. Say these are the values, say either temperature or pressure, or say thickness in millimeter, diameter in millimeter, and so on y-axis. Right. So this dotted line indicate the mean value. Then if now the type 1 is considered, when you are in the calibration phase, you are going to apply the standard input, the block of the given value. Say for example 20 millimeter thickness is given for measurement, or 20 degrees Celsius temperature is applied, or 20 bar pressure is applied, and against which we have got the values on y-axis. Then the true value, if it is known, then we can find very conveniently the systematic error. It is again something repetition of what we studied in the earlier lecture. Right. So systematic error is nothing but difference between the say mean value and the true value, and thus it is going to give the estimation of the precision or including of the bias, it is given the best estimate. And then random error is nothing but the difference between the mean value and the individual measurement that has been carried out. Now, if I am going to see in relation with the measurement, the frequency that I have carried out the measurement number of times, suppose 20 times I have considered measurement, then the spread of data can be shown by means of the bell-shaped curve, where the mean of this line is corresponding to mean of the measurement here. And if I consider now that it is having 90% of chances of uncertainty, then it means that the error will be large. If I consider the measurement to be very precise, only 5% or 10% error, it means that the very few number of results out of this 20 will be considering the given value of the error, and the quantity may lie here near to the mean value. So then in actual practice, we have to consider the randomness. This is going to speak about randomness. So randomness is decided based on the type of the entity under measurement, the accuracy that we want, and so on. Right. So the limit, whether I should be in 1 sigma limit, 2 sigma limit, or 3 sigma limit for randomness into the measurement, that depends on the entity under measurement and the accuracy that it is at. I think this is very clearly known to you now by just correlating the frequency distribution and the measurement pattern that we have carried out. So with this understanding, now let us see this, the numerical. So this is again given in the textbook. Say what is that? Measurement of some resistance, pressure, something, number of times, say 9 number of times it is measured, and it is found that these are the individual readings. Say for example here, for particular experimentation, it is a measurement of the resistance. Okay, so what is the base estimate of resistance? It's very clearly known, it is the mean. And what is the error with 95% of the error propagation? Say mean can be found out. It's very clearly, say here 1.22 is the best estimation of the resistance of data. Once the variance is found out, and then we can have the value of sigma with the use of statistical tool. Now when I say, or somebody is saying that 95% of the confidence of interval is required, then say it is, we know that area under the bell-shaped curve is 1.96 times sigma limit. So this is nothing but a value of the error that is likely to occur if I consider 95% confidence, say 0.038. So similar numericals are given into the number of textbook. Anywhere you can find this kind of numericals, right? So what is we are interested in? Now this is the type 2 measurement where true value is not known, and we are conducting experiment and we want to know how much it is closer to the ideal value, the true value of the input given, right? Then next one, I think it is similar to the data that I already have used in the discussing the properties in the very second or third slide here. So for example, thickness of the metal using some vernier caliper or some micrometer screw gauge is measured 12 number of times, and these are the values obtained. Then what is the variance? So again, the best estimate will be the mean, then variance is found out, then standard deviation, and then 99% of confidence will have the sigma limits. Now actually I was about to find out all the values and discuss with you the expression of the error. Now suppose true value of the error is given. Let us say the mean base estimation is 0.02, and that suppose true value is 0.201 something. Then you also could found out the precision and the additional value. So what I can ask here is, or one can find here is the accuracy or FSR, accuracy over true value, provided true value is known. So from this, if the true value, if I am going to give for that block is 201 millimeter, let us say, then you can find the true value also. If the range of the measurement device, say vernier caliper or micrometer screw gauge is given, say from 0 to let us say 50 millimeters, then this full scale range is known, you can have FSR prediction. Then the third value you can find out here is the bias, then the precision. Once the true value is known, you can find precision. Precision is the difference between the best estimate minus the true value. Then the bias for what is the zero reading. Suppose now one more reading is there for zero, one more value, the 13th value I am going to predict. Say for example 0, 0, 1. In that condition, bias will be equals to this value. That is going to remain constant for most of the reading. Okay. So bias can be found out. Then tolerance band can be found out. The maximum error on the plus side, maximum error on the minus side. Right. So now you can anticipate what we had discussed earlier can be applied to this data. Right. Then variance is found out for 90% of 99% of the it was asked for 99%, but you can say use the value for sigma limit 95%, 99% from the earlier discussion here. Just I will recall the value here. For it is 3.30. For 99%, 2.58. For 0.999% of the error, it will be 3.3. Here 2.58. So then I will jump to the numerical. Using the particular 2.58, you can find out the error that can be present into the measurement device. So for 90%, 2.58. 99%, sorry. It is, I think, for 99%. For 99.9%, the value is 3.13, something that we just now found out from the table. Right. So now today's test that was planned, we are going to take it say tomorrow, not today, will be based on the complete measurement of the calibration, that is type 1, type 2 and type 3 may be given with the true value and not given with the say the general measurement. Right. So let us discuss the part that is called as the drift or the sensitivity error that we already defined. Let us say there is load cell which is to be calibrated at temperature of 20 degrees Celsius. If you recall, before going to this, let me give little say idea about what we discussed for the drift. So for example, the ideal characteristics required is this one, but in actual practice it is going to show some deviation. Say for example 1, that it has deviated because of the drift, say the zero error, or the instead of 0 it is showing some value at 0 input. And say during usage, I think sensitive drift also we have found out that change in the temperature condition or operating condition, it is going to have some deviation from these characteristics. In this one, the characteristics 1 is shifted by means of some value. For the given input, it is going to remain constant, that is we called as a bias. In actual practice, there can be some change in the sensitivity also. The slope may change. So then we have to find the sensitivity error. Now based on this, let us say some information regarding the measurement system is obtained at the given operating and conditions. Say for example, given temperature T, here for 20 degrees Celsius. It shows some load, some value of load. Say initially it was 0, say it is 1, 2, 3, 4, 5, 6. 6 times input is taken. Say input 1, 2, 3, 4, 5 and 6. There are 6 different measurements we carried out. So for first measurement, it is showing 0 or the 0 load. So this is nothing but load. And the deflection in meter, that is output. Deflection in meters. Now when the same test is performed with a temperature condition which is changed, say elevated temperature T dash, say 40 degrees Celsius, then the characteristics obtained for the same input, say for 0, 0.4, 0.8, 0.12, 0.16 and 0.2, say kilonewton, we have got the deflection meters in terms of this value given. So what is required to find? We have to find the zero drift, sensitivity drift and drift per Celsius change in the ambient temperature. Now if the scale division is 0.05 millimeter, can be a fair readout, then we have to determine the resolution of the instrument for both cases of the measurement, say at temperature of operation T0 and T-0, that is 20 degree and 40 degrees. Now for the first one, you can very conveniently find out. Say we go and plot the characteristics of the inputs. Say for the first, second, third, fourth, fifth, and sixth. These are the 6 input that we are given, and we find out the value of the output shown. Say 0, 10, 20, 30, 40, 50, and we can have very clear understanding of the measurement characteristics. We can find out the sensitivity, say change in the output upon change in the input. I think till this point is very clear. It's very normal way. Now then we have gone to the measurement at the elevated temperature. Let us say first of all, we find the sensitivity. So that static sensitivity from the earlier graph I have given, say output upon input, it is going to give some sensitivity in terms of value like millimeter per kilonewton or meters per kilonewton. The output is taken in terms of millimeter. So further, when it is taken at elevated temperature T dash, then we are going to plot another characteristics, maybe the overlapped one. Say because input remains same, there are 6 values of the input, and I am going to find the output for this. Then it is going to show something deviation. So the sensitivity, change in the sensitivity, the slope too can be found out. So output upon the input. So that is found out, say 27.5. Then the sensitivity drift will be the change in the sensitivities at operating temperature T0 and T dash. So that is the difference, say the sensitivity that we obtained at elevated temperature T dash and minus the sensitivity of a instrument at a normal temperature, that is say 20 degrees. So that is 2.5 millimeter per kilonewton is the drift of the instrument. So sensitivity drift for the condition, say 2.5 by 20, that is 0.125 millimeter per kilonewton per degree Celsius. Now what is asked in sensitivity drift per degree Celsius. Now total variation of the temperature from say 20 degrees to 40 degrees. So we have changed the temperature del T equals to 20 degrees. So per degree rise in temperature, what is the sensitivity change that can be found? So total change the sensitivity upon the difference of the temperature. We have found that if 1 degree Celsius is the rise in the temperature, the sensitivity is going to change by means of 0.125 millimeter per kilonewton. Right. Then we also know that inverse of the sensitivity or deflection factor, this also is discussed. We have discussed this into the theory part. So we can find out that in terms of the kilonewton per millimeter, it will just reciprocal of that. Right. Then the resolution. Now this is important. Resolution, when we say, it means that the minimum or the say output indicated by the measurement system per unit rise in the say input entity. So the resolution of the load cell corresponding to the 0.5 millimeter scale reading, say it is millimeter of the scale reading, will be the change in the deflection factor, say 0.04 kilonewton per millimeter into the 0.5 mm. So that is nothing but a 20 Newton is the minimum readout we should have on the instrument. Right. So inverse of the sensitivity, that is going to give 0.036 kilonewton per millimeter as the readout. So similar kind of numerical finds anywhere into the say textbook. So these are very standard problem. Method remains the same. So the resolution of the load corresponding to the 0.5 millimeter of the scale reading, meter scale, that is the display of the element, will be equals to say 0.018 kilonewton, that is 18 Newton. So I think this we have discussed regarding the experimentation. What is the full scale reading? I will again iterate. 10 kg is the load cell full scale load value for experiment number 1 and experiment number 2. That is the force and the torque measurement using the strain gauge based device. For linear displacement, it is 0 to 300 degrees graduation on the say angle measurement range, and for linear it is 50 millimeter the scale reading. So the full scale reading is 5 centimeter or 50 millimeter for experiment number 3. For experiment 4, it is a speed measurement. So maximum speed of the motor that can be achieved, you might have seen in the experimentation, is 32 RPS. So for experiment number 4 as well as 5, you have got the same value. Right. Now I also have discussed how to find the non-linearity here. The hysteresis curve and how to find the non-linearity, that also has been discussed. Okay. So now one more important element here before going to the next part, just to discuss. Okay. For timing, I will remove up the things here. I'll use this as a blank slide. Something regarding the regression analysis. That is what you need to do by your own. I hope you have gone through somewhere in your study the regression analysis. If you recall, in the discussion, we have said that the linearity can be expressed in terms of the percentage over the full scale deviation. And suppose now you are carrying out the measurement for say 10 different variations, say 1, 2, 3, 4, 5, 6, 7, 8. Suppose now 8 times you have taken the reading by changing the input, and each time you have got some value that is say indicated here by means of some output. Right, so these are the actual findings of your output. Now this can be expressed in terms of the deviation of the actual performance curve if I am going to join with the help of lines. This is the actual performance of the measurement system, and the ideal performance of this system is nothing but the one that can be shown by means of a line passing through this. So this can be best known by having the regression analysis. I think you can go through the different textbooks if you are not recalling how you have carried out regression analysis. With the help of regression analysis, you have found out suppose the best fit line that is passing through between the all measured entities. So this indicates the best fit line. And then you have to find out the deviation. Let us say the deviation between each individual reading. Say this is, for example, this is the reading number 5th. Say let us say this is one reading here. So the deviation here is this between the base fit line x coordinate, the base fit line y coordinate and the actual y coordinate for this reading. So this is the deviation. So this is nothing but x6. I will call this as error Ex for reading number 6, and then I can predict the other properties like the maximum non-linearity of this graph. Suppose it is occurring, maximum deviation occurring here, then it will be found out and we can specify that Ex for the given ith reading over the total range of the instrument. That is, say for example, it is going to read from 0 to 8 bar as the maximum range of that instrument. So then it will be 8 bar into percentage. So we can specify this as a percentage non-linearity. So again, I am catching your attention to the regression analysis. So you might not be knowing about how the true line is to be drawn. So you go and find it out. So your test or at some place we can have the numericals where you are going to carry out regression analysis and do the further static characteristics, say identification or estimation. So let me go to the next one. Okay, so then we'll go to the next part, that is the overall system accuracy prediction. Whether I have shared with you. Any doubt to this point? Let me know. Anything that is not clear? why these students are appearing too late into the classes? It's already 11:40. Around 40 minutes we have consumed. Now, please let me know any difficulty in understanding the portion that we have discussed till this point of time. So we'll go for discussion on this overall system accuracy. Now let us understand what is the how we arrived to this word, how we are going to correlate this called the overall system accuracy. In the earlier slides before this particular presentation, what we have studied is the experimentation phenomena, maybe calibration or experimentation for a single entity. So for example, all the numericals that we have studied or we are going to find out from the textbook or somewhere, they were related to measurement of single entity. Let it be temperature, let it be pressure, let it be the say the physical length, diameter, and so on. Measurement of any single quantity. And then we have found out the characteristics of the static characteristics of the measurement system. But in actual practice, we find that the entities are derived. If you recall the discussion on the standards and the other practices for measurement, we have said that there are fundamental units or fundamental entities for measurement and derived entity. I think if you can correlate. So let us say that there is an entity called as an area, and in your experimentation, you are going to find out the area of certain component which is required for your experimentation or for measurement. Say for example, measurement of the flow of the fluid, measurement of the pressure. You need to find out the area of the quantity under measurement. The area of a system must be known, so which is nothing but the typically length into the width, or say L into T. You can use any notation. So it means that you need to have measurement twice for length as well as for thickness. If it is a round area, element, then it is with some equation where D is the diameter. You are going to have one measurement. But now the measurement, suppose that is carried out by using vernier caliper or micrometer screw gauge for length and width or the diameter or length of some arm, something like that, then it will have the accuracy. So you have carried out the experimentation, you have taken 20 readings for diameter, suppose. Let us think of having the area of a bar, a circular bar. And you found out that the accuracy is suppose 0.1 millimeter over 20 millimeter diameter of the bar. So it is 20 plus minus 0.1. Now when you will calculate the area, what is the accuracy of the area measurement? Say, will it be say plus minus 0.1? Say for example, pi over 4 d square, I have found out something. Let us say hypothetically I have found that it is 40 millimeter square is the area. This is what I have found from the notional values into account for the system accuracy, the measurement entity accuracy. But what about the uncertainty? What about the error that is going to propagate? Will it be 0.1 only, or will it be 0.1 square? What is that? And how to find out? So this plays an important role. It is say not only the measurement point of view from different properties, but it happens into the actual shop floor. I don't know whether you are going to come across this thing somewhere or you have gone through. So let us consider an example where on the shop floor you are going to measure the length of the step shaft. Say this is a bar of diameter something, say 20 millimeter here, 520, here it is 510, and the length is given. Ideally, as a designer, your specified length of this bar should be equal to 50, and then this is plus minus 0.01 millimeter. And as a designer, here you are specified that this should be equal to 45 with an accuracy of plus minus 0.01. Now, if you are going to measure the total length, then what will be accuracy? Length you can find out. So I am going to write here L, and plus minus what you are going to write here. It's question mark. then you must know how the uncertainties are accounted for into the system, into the measurement devices. Here it is very simple that you are going to use either vernier caliper or micrometer screw gauge. It's a very simple measurement on the shop floor. But you can understand the different methods, different entities which are derived entity, as well as it is having multiple functions into it. Are you able to correlate this? Where from how we are going to move ahead? We are concerned about the mechanical measurement of the mechanical entities, say temperature, pressure, and so on. How the error goes on amplifying further. That is what is important. Have you gone through this kind of addition, subtraction, and so on in the metrology part? Please let me know. Any one of you can answer. Am I audible? No, ठीक है. If I am audible, you can give some voice input to me. Kalyan, I think you are on some traffic somewhere. You can give voice note to me. I'm say more eager to see or hear your voices. Is it so difficult for somebody to answer it in say some voice format? Please answer this query. I want some answer from you, not in the chat format. You give some voice answer so that I can have some discussion on it. What happened? Aditya, am I audible? Only I know the particular student name. I can ask at least to him. Aditya, am I audible?
Yes, sir. Yes, sir. You're audible.
Then why nobody is giving any answer to me? I'm not getting. What I asked is whether these kind of things you have gone through, addition, subtraction, and so on of the say entities you have gone through somewhere.
Yes, sir.
Okay, multiplication and division also you have gone through.
Sir. Yes, sir.
So shall I consider that you know everything about addition, subtraction, multiplication, and division of this?
Yes, sir.
So why if it is so much time required for giving this answer to me? Anyway, so that's what my discussion is, how we are going to have the uncertainty into the measurement. So if the accuracy of the measurement system is to be found out from the known component inaccuracies, combination of the errors or uncertainties is very essential. The component errors or uncertainties are expressed as plus minus limit of the full scale measurement is also known to us. So it includes all kind of error. So once we have quantified that how much is the random error, how much is the say bias and so on, the numerical value whatever you got in plus minus limit, that we have to consider and move ahead for the measurement system say calibration or measurement system characteristics establishment, right? So there can be say overall system inaccuracy. That's what I was about to take your attention. It is to be added or subtracted and sometimes multiplied and divided. So now as per your feedback anyway, you are knowing this, so we just correlate that. It's very simple. If the two entities are derived out of say one entity is derived out of 2 or 3 different measurements, say for example area and volume is the entity that has been derived out of the diameter length or length, width and the thickness, say for example volume. We can find out what is the uncertainty if the individual error for measurement is known. So here it will be multiplying. Now if it is length, total measurement of the step bar, then you are going to add and subtract the uncertainties. So I will not be able to go in detail of this one, how those are added and subtracted. Okay, so there is, now let us understand this first. Apart from these derived entities, there are some phenomena. Say for example now finding say power of IC engine or power given by your motor, electric motor. Let us say this is an entity under measurement. You have to find out power. Now what is the component into this power? You have got different elements. Say it is twice pi nt by 60 or something. The equations are there. It means that there are multiple measurements. Measurement of, say, this 60 is related to the revolution. So if this is in RPM, so it is measurement of the speed, measurement of the torque, measurement of the say time, and so on. So there are this very simple equation I have taken. Let us take into flow measurement. You have got some equation. Right. So when these expressions are giving the total phenomena that is governed with different single individual entities, we need to find out how the error goes on propagating. Okay, I think I will continue for another 3-4 minutes and then we'll have some discussion on your test. So the accuracy of the measurement system is to be found out from known component inaccuracies. Say for example inaccuracies or uncertainties into measurement of the speed, of torque. Then actually this torque is nothing but the force into the length of some r. So uncertainties associated with measurement of the length, measurement of the forces, measurement of the speed are to be found out individually. That is what we can do. We can have the different measurement system for length measurement, force measurement, speed measurement, that is in terms of RPM and so on. And then we have to combine those. So combination of the errors is necessary. Now the component error will be expressed in terms of plus minus limit of full scale measurement. Say for example, force measurement plus minus some error. Length measurement, it will have plus minus some inaccuracies into it. While measuring the speed in RPM or RPS, it will have some plus minus value of the variation. There is some error in measurement. So that it is inclusive of all the errors. Let us say now the total entity of the system, say for example power here, is a function of individual factors, say U1, U2 and so on, where these are the n number of entities here. Say for example into this expression there are 1, 2, 3 entities under measurement. So here n will become 3. So each of the uncertainty is required to be taken into account. So the error or uncertainty into the total value of the final derived quantity, say for example power here. So plus minus accuracy or uncertainty of the power measurement will be the function of uncertainty into the very first entity under measurement, say for example here the speed, as well as the subsequent values. Say next is here the force measurement. Again force is nothing but mass into the acceleration. That is, say, sometimes you will have the different measurement system directly giving force, or you then find out that will be expressed in terms of some other entities also. So uncertainty into the force measurement. Then there is a third entity, that is length. Say for example the length and the uncertainty into length measurement, so on. So what we can understand is the total uncertainty in the overall system will be function of uncertainties on each individual components under measurement, whereas plus minus del n is the inaccuracy of the total system measurement, and del u1 u2 are the inaccuracies of the individual components. So with this understanding now we can find out that the total uncertainty in the output value, the overall system accuracy will be equals to the one with deviation minus the ideal, that is without deviation. It's very clear to understand. So this can be done by having, say for example, f is function of the ideal uncertainties like u1 plus minus del u1, u2 plus minus del u2. Then we can go for using the Taylor series of expansion. Say for example, the uncertainties, the ideal components plus uncertainties and their higher derivatives. Now as we go on having this power, raising power, you will find that this entity is going to become smaller and smaller. So this is what is called as the Taylor series expansion for the error propagation. We are using this here for the uncertainty estimation. Now we consider that this value of square, cube and so on, the higher terms are going to be smaller and smaller, and thus we neglect. So this neglecting this particular component, we can find the uncertainty will be given in terms of absolute error, say EA, that will be equals to the del U1 into function with respect to the uncertainty 1, partial derivative with respect to uncertainty 2, and so on. So once if we find this kind of partial derivatives, we can express the total uncertainty that is going to be predicted in terms of the total accuracy or inaccuracy of the system. So the error will be equal to del n upon n, and it will be expressed in terms of percentage. So I think I will restrict my discussion here. Now the test, there were some questions yesterday on the groups, and even some students asked me. I have not given any answer because I was not sure how much portion that we will cover today. So better we will have the test tomorrow. Any problem in conducting test tomorrow instead of today? So what I want is you go through textbooks and find out at least some numerical treatment. That was already told to you in the last lecture. But let us have the test instead of today, tomorrow, the same time, 6 o'clock.
Okay, sir.
So with this say understanding and the agreement, we'll have the test tomorrow, and we'll continue from this slide onward in the next lecture.
Sir,
Yes, please go ahead.
sir, I just had a small doubt.
Yeah.
Sir, in regression analysis, when you had mentioned, sir, that particular formula that was there, that is there only for a particular point, right? Like error at particular point 6, the standard deviation that formula, to find the percentage non-linearity.
Right.
Sir, so if you want to find total percentage non-linearity of an entire graph, then do you use the combination of errors that you've thought right now to calculate that, or?
No. Total uncertain, say non-linearity into the system will be given where the maximum randomness is considered. So for example, there are 10 readings, and out of 10 readings, wherever maximum deviation from the best fit line is found out, for that reading only we consider, and that we consider as the maximum non-linearity present into the system.
Okay, sir. So it's only for the maximum deviation point, nowhere else.
Yes. It's
Okay,
only
sir.
maximum prediction of the non-linearity. I am saying particularly about non-linearity.
Yes, sir. Right, sir. Got it. Thank you, sir.
So there is no doubt. I think we will stop here for today. Please ask doubt by even the tomorrow's class. Thank you for joining.